All right, let's dive into one of the weirdest, most mind-bending concepts in all of physics, quantum entanglement. It's this idea that there's a hidden layer to reality, a deep connection linking tiny particles together no matter how far apart they are. So let's get into it. And the best place to start is with the guy who gave it its famous nickname, Albert Einstein. I mean, this is a giant of physics, and even he was totally freaked out by entanglement. He called it spooky action at a distance because it seemed to break the rules of the universe that he himself helped write. And honestly, his skepticism kicked off one of the biggest debates in the history of science. So, what exactly was so spooky to Einstein? Well, in this first part, we're going to define what this thing actually is and figure out why it completely rocked our old-school classical view of how the world works. Okay, so here's the core idea. Imagine you have two particles that bump into each other and become linked. They basically stop being two separate things and instead behave as one single system, sharing one quantum state. Now, here's the wild part. That connection sticks around no matter how far apart they get. We're talking across the room or even across the entire universe. And this really shows you just how different our everyday world is from the quantum world. In our classical view, things are separate. If you want to influence something, you have to send a signal, right? And that takes time. But in the quantum realm, these entangled particles act like a single unit. The connection is non-local, which is a fancy way of saying it's instantaneous. It doesn't need a signal, it just is. This points to a reality that's way more interconnected than we ever thought. So now, let's dig into how this unbreakable link actually works. And while we're at it, let's tackle the biggest misconception that always comes up with this stuff. Okay, here's a classic example just to make this a bit more concrete. Let's say you have two entangled electrons. You can think of their spin as a property that's either up or down. Since they're entangled in a specific way, if you measure one of them and find its spin is up, you know instantaneously that its partner's spin is down. It's a perfect one-to-one correlation. So the big mystery is, how does that second particle know what happened to the first one? Instantaneously, even if it's light years away. And this right here brings us to the million-dollar question. This is the thing that really bothered Einstein. If the effect is instantaneous, can we use it to send messages faster than light? Can we break the cosmic speed limit? The answer, and this is a big one, is no. You can't. While the connection is instant, you have absolutely no control over the outcome. You can't force the first electron to be up just to send a 1 to your friend. The result is random. You only find out what it is when you measure it. And for your friend to know that their particle's result is correlated with yours, you still have to pick up the phone or send an email, which of course is limited by the speed of light. So reality is safe. Causality is intact. So if it doesn't break relativity, what was the big deal? Well, this next part is all about the epic scientific clash that took entanglement from a weird philosophical idea and turned it into a cold, hard fact of nature. This timeline really tells the story perfectly. It all started back in 1935 when Einstein argued there must be some hidden variables, like secret instructions the particles carry with them. For decades, it was just a debate, but then in 1964, a physicist named John Bell came up with an amazing mathematical test. His theorem basically said, okay, if Einstein is right about these hidden variables, then the results of experiments can only be correlated up to a certain point. And guess what? Starting in the 70s, experiment after experiment showed that the universe violates Bell's limit. The universe is just stranger than we thought. And the ultimate confirmation, the final word, came in 2022. That's when Alain Aspect, John Clauser, and Anton Zeilinger won the Nobel Prize in Physics for their brilliant experiments that finally settled the debate. So, while Einstein's intuition was incredible, in this case, the universe proved to be even more mysterious and, well, spooky than even he could have imagined. Proving entanglement was real was just the start. Now, we're actually learning how to use it. So let's look at the incredible quantum revolution that this spooky action is powering today. First up is something that sounds like it's straight out of science fiction, truly unhackable communication. We're talking about a level of security that isn't based on complicated math problems, but on the fundamental laws of physics itself. It's called quantum key distribution, or QKD. The idea is brilliant. You use entangled photons to create a secret encryption key. Now, if a spy tries to intercept one of those photons to read it, the very act of measuring it destroys the entanglement. It's like a tripwire. That disturbance is immediately detected, and you know someone's listening in.
This isn't just theory either. Satellites like China's Mischius are already using this to send keys over huge distances. Next up, a concept that everybody loves, quantum teleportation. But let's be super clear here. We're not talking about beaming people from place to place like in Star Trek. What we are talking about is transferring quantum information in a way that's, well, pretty remarkable.
Okay, so here's how it works. Step 1. Alice, the sender, and Bob, the receiver, each get one particle from an entangled pair. Step 2. Alice takes the quantum state she wants to teleport and does a special measurement on it and her entangled particle. Step 3. She then sends the result of that measurement, just normal data, to Bob. Step 4. Bob takes that information, does a little operation on his particle, and boom, his particle transforms into a perfect copy of the state Alice wanted to send. Mind-bending, right? And finally, we've got the application that could literally change everything. Quantum computing. This is where entanglement opens the door to a whole new world of processing power. So your laptop uses bits. They're either a 0 or a 1. Simple. Quantum computers use qubits, and they can be a 0 and a 1 at the same time. But when you entangle these qubits, they can work together to explore a ridiculous number of possibilities all at once. This means they can solve certain problems like discovering new medicines or breaking modern encryption exponentially faster than our best supercomputers. And with milestones like Google's quantum supremacy, we know this is happening now.
So where is all this going? I mean, we've gone from a philosophical headache for Einstein to a technology that is fundamentally changing our world. Let's take a peek at what our entangled future might look like.
When you step back, it's an incredible story. Quantum entanglement has transformed from this strange, spooky feature of physics that bug the world's smartest man into the engine that's driving the next great technological revolution. It's just an amazing reminder that when we probe the deepest mysteries of the universe, we can end up with the most powerful tools. And believe me, the story is nowhere near finished. Some of the wildest theories in physics today suggest that entanglement might be even more fundamental than we think. There's this idea called ER equals EPR, which suggests that wormholes in space-time might actually be entanglement. Think about that. The very fabric of space and time could be woven from these tiny quantum threads. It means our universe isn't just a bunch of separate things, but a deeply, fundamentally interconnected network. Which leaves us with a final massive question. We've proven these hidden connections are real, and we're starting to use them. But if entanglement really is the fabric of our universe, what does that actually mean for the nature of our reality? What other secrets are hiding out there in that spooky, connected space?